Hello class. For this lecture we're going to go over units 23 and 24, which is on resistive, inductive, and capacitive series and parallel circuits. So basically what we're going to do is take all three of our major circuit values of resistors, inductors, capacitors, and combine them into a circuit. And really anything, pretty much anything in the world, if you apply it to a circuit, it can be modeled as a combination of these three different components. So for the most part, these two units will be sort of review of pretty much everything we've gone over before in all previous units of the class. So let's go ahead and review each of our major circuit components. First, we have a resistor R. Remember, resistor R consumes true power P. True power is the power of a circuit that can actually be utilized or converted to some other form. The relationship for voltage and current when it goes through a resistor are that the voltage and current are in phase or also 0 degrees out of phase with one another. That means that the voltage and the current both start at 0 at the same time, they both hit their maximum peak at the same time, hit 0 again at the same time, so on and so forth. Next, we have an inductor. Inductor symbolized by the letter L. An inductor consumes reactive power, bars L. And for an inductor, a purely inductive circuit, the current lags the voltage by 90 degrees. By lags, we mean it happens after the voltage by 90 degrees of time. Remember, when we treat time, we're dividing it into units of degrees instead of seconds. It's just another unit we're getting for time. And so we have the voltage start at 0 at time t equals 0 or 0 degrees, and we notice that the current doesn't have its 0 crossing until positive 90 degrees later on the sine wave. Finally, we have our capacitors C. They consume reactive power, also symbolized by the letters bar C. And then for a purely capacitive circuit, the current leads the voltage by 90 degrees. So by leading, we mean before the voltage. So we go negative 90 degrees over here, and the current has its 0 crossing negative 90 degrees before the voltage has its 0 crossing. Okay? And because of these different relationships between voltage and current, between the resistor, inductor, and capacitor, we have to treat them, their associated values, as vectors. So a sort of general vector form for resistors, inductors, and capacitors is something like this. Here, for any type of resistive value, we have all the values at 0 degrees for our vector. Any inductive values we put at positive 90 degrees. And then any capacitive values we take to be at negative 90 degrees. And this is true for all related values. So any inductive value like inductive reactance, X sub L, the reactive power for an inductor, bars L, those will all be at positive 90 degrees. Now I know in the textbook they treat the current vector for capacitors as a positive 90 degrees and the current value for inductors at a negative 90 degrees. That is correct, and there's a subtle reason for that I don't really want to get into in this class. It's sort of more for the engineering side of things. And so to keep things simple, we can treat all inductive values as a vector pointing up and all capacitive values as a vector pointing down. Like I said, there is that slight subtle difference with the current vectors, but it's not going to matter mathematically when we're actually solving these circuits. Just to keep things simple in this class, we keep all inductive values at positive 90, all resistive values at 0 degrees, and all capacitive values at negative 90 degrees. So if we are going to have circuits that combine all three of these, once again, we need to treat them as vectors, and we have to see how they combine. So in the case of something like our power values, once again, we'll have the resistive type of power, which would be our true power at 0 degrees, the reactive type of power for the inductor, bars L, at positive 90 degrees, and the reactive type of power for the capacitor, bar C, at negative 90 degrees. Now let's say we need to combine we want to find the total bars of the circuit. If there's going to be a circuit, let's say a circuit like this, the resistor, an inductor, and a capacitor. The resistor has some true power P, the inductor has some reactive power bars L, and the capacitor has reactive power bar C, and we want to know what is the total reactive power of the circuit. So if we want to know this, we have to treat them as vectors. Now remember, vectors that are direct opposite of one another means we simply subtract them. So the total bars would be the vector of the value of bars L minus the value of bars C. The same thing is true for our impedance values, or our ohmic values. A resistor has resistance R, an inductive circuit has inductive reactance X sub L, and a capacitive circuit, or capacitor, has an ohmic value of inductive reactance X sub C. So the total reactance of the circuit, XT, would be equal to X sub L minus X sub C. So once again, a vector going up plus a vector going down means you simply, technically you should be adding these, so it should be X plus negative C, like this, if I want to be mathematically rigorous. Remember, a vector pointing out, we give a positive value, and a vector pointing down, we give a negative value. But a positive plus a negative value is the same as just subtracting, like this. So that's our review for the different types of circuit components, of resistors, inductors, and capacitors. Let's go ahead and start solving circuits. So bear with me now while I get a series circuit drawn up on the board. A little more space here. Okay, so here's our series resistive, inductive, capacitive circuit. Here are all the circuit values that are given. Now let's go ahead and solve the rest. So all the equations that we've been using previously in the class still hold true. The only thing that's going to change, and as you guys have probably noticed, is the equation for impedance. This has always kind of changed for every type of circuit that we've been looking for. Depending on what the circuit contained, what the configuration was, this equation is always sort of changing. Everything else, the equations all stay the same. And so, we have a series circuit with one path for current to flow. So we know that if it's a series circuit, there is only current is the same everywhere. I have given you the current through the resistor is 12 amps. That has to mean that the current through the capacitor is 12 amps. The current through the inductor is 12 amps. And the total current being supplied by the AC source also has to be 12 amps. So if you have one current value, you have the rest. Actually, let me use red here, so that shows up better on the video. That should always be the first thing you try to go for in a series circuit is find the current. Can I get the current on the rest of the values? In this case, I've made it easy and already given you one of the currents. Next, it just comes up to choice on what we want to solve for next. I'm going to start with the resistor first. Find the voltage drop across the resistor, E sub R, go to Ohm's law, will be I sub R times R, 12 amps times 12 ohms, gives me 144 volts. I'm going to save all power values for last. So next, let's deal with the inductor. The inductance, L, is equal to 2 pi times the frequency times the inductive reactance. Oops, no, I'm sorry. Got my equation mixed up. L is equal to the inductive reactance divided by 2 pi times the frequency. Once again, if the frequency is not given, always assume that it is 60 hertz. So the inductance is going to be 24 divided by 2 pi times the frequency of 60 hertz. And that gives me 0.0637 Henrys. Next, the voltage drop across the inductor, E sub L, due to Ohm's law, would be I sub L times X sub L. So 12 amps times 24 ohms gives me 288 volts for E sub L. Save the reactive power for last. So next, let's deal with the capacitor. The capacitance is equal to 1 divided by 2 pi times your frequency times the capacitive reactance. So that's 1 divided by 2 pi times 60 times 8 ohms. Throw that on our calculator. Let me grab a calculator. and that gives me a capacitance value of 0.003316 farads. On the test, it is fine if you leave your answer like this. However, we typically always give capacitance values in microfarads. And so to do it in microfarads, micro means times 10 to the power negative 6. So I've got to take my decimal place and go 6 places to the right. So that would be a capacitance value of 331.6 microfarads. Next, the voltage drop across the capacitor, E sub C. Current through the capacitor applied to the capacitor by the capacitive reactance. So 12 amps times 8 ohms gives me 96 volts. Next, let's deal with the total voltage. So let me redraw this vector relationship right here. And now let's look at the total voltage. The total voltage, due to Ohm's law, would be the total current multiplied by the impedance. However, we do not have the impedance Z. What is that? As you might guess, it is an utterly, well, it's not too bad. It's not too disgusting of a formula. So once again, we need to treat each of these individual values as vectors. So it's going to be something related to Pythagorean theorem. Since we're going to be creating triangles, it's going to be r squared plus x sub L minus x sub C squared. So remember, any vectors that are directly opposite one another, we're going to subtract them. So we're going to have the vector x sub L at positive 90, the vector x sub C at negative 90 degrees. They're directly opposite one another, so we're going to subtract x sub C from x sub L. So this one isn't too difficult. So this is going to be the square root of 12 squared plus x sub L is 24. We're going to subtract x sub C, which is from 8. So that's going to give us 16, which will give us a total impedance of 20 ohms. So, total voltage is going to be 12 amps multiplied by 20 ohms, which should give you 240 volts. However, let's check this answer. let's say we don't want to use, we want to check our answer, or we don't want to use this nasty equation. There's a way to avoid using this equation, and that is through Kirchhoff's voltage law. Kirchhoff's voltage law states that the sum of the voltage drops across each individual component should equal the source voltage. Of course, this is going to be the vector sum of each individual component, so the total voltage is going to be equal to the vector sum of the voltage drops across each component, so that's going to be the square root of ER squared plus EL minus EC squared. So this is equal to the square root of 144 squared plus EL is 288. I'm going to subtract EC, which is 96 volts, and that gives me 192 volts. Throw that into my handy dandy calculator. And that gives me a value of 240 volts, which was the same value I found using Ohm's law. So we are all good so far. Now, let's deal with the power values. So the true power, P, is equal to ER times IR. So 144 volts times 12 amps. That gives me 1,728 watts. The reactive power of the inductor, R is L, VEL times IL, 288 volts, times 12 amps, 3,456 bars of reactive power. Next, the reactive power of the capacitor, RLC, is going to be EC times IC, 96 volts times 12 amps, 1,152 bars. And then finally, our apparent power of the circuit, which can be thought of as sort of the total power being provided by the circuit. That's going to be ET times IT, the total voltage multiplied total current. So 240 volts times 12 amps gives me a total apparent power of 2,880 volt amps. Let's check. Law of conservation of energy states that the total power being supplied by the circuit should be equal to the powers being consumed by each individual component. So that means that the apparent power should be equal to the sum of all the powers across each component. Once again, we must treat these as vectors. So this is going to be equal to the square root of the true power squared plus the reactive power to the inductor minus the reactive power to the capacitor squared. See what we get. So this is the square root of 1,728 squared plus the vector sum of the two reactive powers. So 3,456 bars minus 1,152 bars gives me a total reactive power 2,304. Throw this on our calculator. And that gives me a value of 2,880, which is the same amount we found using, which is essentially a form of Watt's law. Remember, Watt's law essentially states that the power can be found by multiplying the voltage times the current. Okay. Let's write my answers down on my answer key. Next is the power factor. Power factor is your ratio of your true power P divided by your apparent power PA. It lets you know what percentage of the circuit, of the power being produced in the circuit, can actually be utilized or converted to some other form. True power P is 1,720 watts. Our apparent power is 2,880 voltamps. And I get a power factor of 0.6, which is also equal to 60%. So 60% of the power being produced by the circuit can actually be converted to some other form. And then finally, we have angle theta, which is the relationship between voltage and current, the phase relationship between voltage and current. It is the arc cosine, or the cosine to the power -1 of your power factor. So you take your power factor, the decimal value, and plug it in right here. Make sure you're using cosine to the power -1 and not just cosine on your calculator. And that gives me 53.13 degrees between the voltage and the current. Now, technically, we need to identify the type of power factor and the type of angle theta. And what do I mean by that? What I mean is that is this circuit more inductive or is it more capacitive? So if the circuit was more inductive, it would have a lagging power factor, and if the circuit was more capacitive, it would have a leading power factor. So the easy way to figure this out is to look at the reactive power value between your inductor and your capacitor. So the reactive power for our inductor is 3,456 bars. The reactive power of our capacitor is 1,152 bars. Which of these two has the higher value? It is, of course, the capacitor or the inductor. And so we would say the circuit is more inductive than it is capacitive. So the power factor would be lagging. Remember, lagging goes with the inductor because current lags the voltage. Same thing here. We would have a lagging angle theta as well. And so, in another case, if the capacitance, there was more capacitive reactive power than inductive reactive power, that if this number was greater than this number, then we would say we would have a leading power factor and a leading angle theta. I'm not going to expect you to do that on a test. It's just something I want you to know on future reference, and it's actually incredibly important in engineering and when designing stuff. So I just want you guys to know how to identify that factor. The easiest way is to just look at the reactive powers between the two. Which one is greater? And remember that lagging goes with inductance and leading goes with capacitance. Okay, so that completes a resistive, inductive, capacitive series circuit. So let's go ahead and get a parallel version of the circuit on the board. So bear with me while I get that on the board. Okay, so here is our resistive, inductive, capacitive parallel circuit. And this is all I've given you, so find the rest. Parallel circuit, we all know that voltage stays the same. And so, since we have 120 volts at the AC source, we have to have 120 volts across the resistor, 120 volts across the inductor, and 120 volts across the capacitor. And so, let us find the rest of the values. First, the resistor. The current to the resistor, IR, due to Ohm's law, would be the voltage across the resistor divided by the resistance. So 120 volts divided by 12 ohms gives me 10 amps. Next, looking at the inductor, I know that X sub L is equal to 2 pi times your frequency times your inductance. Oh, and once again, let me remind you that all the equations that we've been using have stayed the same. As you might guess, the equation for the impedance Z will change, but everything else is the same as far as our equations. So X sub L, the inductive reactance, is equal to 2 pi times your frequency times your inductance L. I algebraically solve this equation for L, and I get that L is equal to the inductive reactance divided by 2 pi times your frequency. So that is equal to 16 divided by 2 pi times 60. Which gives me an inductance of 0.04244 henries. Next, the current through the inductor, I sub L, E sub L, divided by X sub L, so 120 volts, divided by 16 ohms, gives me 7.5 amps of current through the inductor. Next, the capacitor. Capacitance C is equal to 1 divided by 2 pi times your frequency times the capacitive reactance. So that is 1 divided by 2 pi times 60 times a capacitive reactance of 8 ohms. And that gives me a capacitance of 0.003316 farads. You always typically like to have capacitance values in terms of at least microfarads. So micro means times 10 to the power -6. So I'm going to take this decimal and go 1, 2, 3, 4, 5, 6. Places to the right. That puts my new decimal point there. So to write this as micro, I would say it's 331.6 microfarads. And now the current through the capacitor, IC, is equal to EC divided by X sub C, so 120 divided by 8 gives me 15 amps. let's check our current values. Actually, no. First, let's find, before we check all our current values, let's find Z. Let's deal with the nastiness. That is the impedance Z in an RLC parallel circuit. So the equation for the impedance in an RLC parallel circuit is this, and I have to write this down because it is the most absolutely disgusting equation in the entire class. It is equal to 1 divided by the square root of 1 divided by r squared plus 1 divided by x sub L minus 1 divided by x sub C squared. That is abso-freaking-lutely terrible to put into a calculator. I will not expect you guys to do this at all. I would never use this. There are simpler ways to find the impedance, and that is through good old Ohm's law, which is simply the total voltage divided by the total current. However, problem is we do not have the total current given in the circuit, so how else would we find the total current? You can also find the total current through Kirchhoff's current law. Kirchhoff's current law states that the total voltage being supplied by the circuit should be equal to the sum of the individual currents through each branch. In this case, it's going to be a vector sum. So the total current would be equal to the vector sum of the current to the resistor plus the currents to the inductor and the capacitor. So it's going to look something like this. So this is equal to the square root of 10 squared plus 15, or 7.5 minus 15. So 7.5 minus 15 gives me negative 7.5. That is okay if you get a negative value. Why is it okay? Because once you square a negative value, it still becomes positive anyways. Throw that in our calculator. I'm sure you guys can see by now why I had you guys practice Pythagorean theorem so many times. That's because it shows up so many times when doing circuit analysis in AC circuits. And so I get a total current of 12.5 amps. So that now allows us to find total impedance. It's going to be 120 volts divided by 12.5 amps, which is 9.6 ohms for our impedance of the circuit. Next, let's deal with the powers. So the true power P, due to Watt's law, would be resistive voltage multiplied by the resistive current, 120 volts times 10 amps, gives me 1,200 watts. Next, the reactive power of the inductor, R is L, EL multiplied by IL, which gives me 900 bars of reactive power from the inductor. Next, the reactive power from the capacitor, RC, would of course be EC times IC. So 120 volts times an inductive, or reactive, or sorry, capacitive current. That's how many currents in the circuit. So 120 times 15 gives me And then finally, the apparent power, VA, which can be thought of as the total power of the circuit. So we're going to take the total voltage and multiply it by the total current. So 120 volts times 12.5 amps. That gives me 1,500 volt amps of apparent power. Next, let's check the law of the conservation of energy. The energy that you put in should be the energy that you take out. In this case, we're looking at power, which is energy over time. So does the total power being, or the apparent power of the circuit being supplied equal to the power of each individual component? This looks a little funky because we have 1,500 volt amps from the total power of the circuit, but the capacitor has what seems like even more. I mean, that seems sort of unintuitive. Is that real? Does that actually work out? Well, let's check. So we take the vector sum of all the individual powers. So that's going to be, oops, before I write numbers down, let me run it out symbolically. So that's the true power, P squared, plus bars L minus bars C. We're taking the vector addition of all the individual powers. So this is the square root 1200 squared plus bars L minus bars C. So bars L is 900 volt amps, and we're going to subtract bar C, which is 1800 volt amps, which should give us negative 900, and then we square it, take the square root. And that gives us a value of 1,500 volt amps, which is the same value we found using Mach's law. So why is this possible? Why are we getting more reactive power than the total apparent power of the circuit? That has to do, once again, with the relationship between inductors and capacitors. Inductors and capacitors, since their vectors are in direct opposition of one another, essentially cancel each other's effects out. So even though we're producing 1,800 bars on the capacitor, it's getting 900 of those bars is getting canceled out by the inductor. And so when we do still add up all the powers, we still get a total apparent power of 1,500 volt amps. Next, power factor, which is the true power P divided by the apparent power VA. That gives me 0.8 or 80%. So 80% in the power being produced in the circuit can actually be utilized or converted to some other form. And then finally we have angle theta, the phase difference between the voltage and current sine waves, which is the arc cosine or cosine to the power -1 of your power factor. Once again, please make sure that the decimal value of your power factor and not the percentage value. So this is cosine -1 of 0.8, which gives me an angle of 36.87 degrees. And now, technically, we should also state, is the power factor lagging or leading? If it's more inductive, it is lagging. If it is more capacitive, it is leading. The easy way to find this out is looking at the reactive powers of each reactive component. So that the inductor has a reactive power of 900 bars, The capacitor has a reactive power of 1800 bars. 1800 is of course greater than 900, so the circuit is more capacitive than it is inductive, which would mean that we have a leading power factor and a leading phase angle between voltage and current. And so that completes our lecture for RLC parallel circuits. Thank you for watching.